All right, guys. Hey, my name's Chris Murphy. I want to thank you guys for coming out tonight for the inaugural official Raleigh Docker Meetup. This is our first, so thank you very much for being here. All the other meetups, I don't know if you guys have been meetup members before, but usually in the beginning we have a time. Anybody has any positions they want filled or has any announcements, give you guys the time to talk. Is there anybody? What was that last one?
MySQL DBA.
All right. So is that a hand raise or? Okay. All right. We'll go ahead and get started. Jerry Arms is going to talk about performance testing, and I'm going to pass the mic over to you. Thank you all very much.
All right. Thanks, Chris. One of the gentlemen in the 101 just now asked to attach arbitrary metadata to a Docker image. It's not upstream, but the code is written and waiting in a pull request.
Wow.
So.
Just for you.
Yeah, we wrote that pretty quick. Yeah, no problem. No, because we've wanted that for so long.
Somewhere, but
Yeah.
I couldn't remember where.
Yeah. Cool. All right. Also, this is my first time using slides.com or reveal.js, whatever. So I apologize if there's any bugs in this presentation. The deck itself is, as I said, on slides.com, and the code that comprises the demos is on GitHub, and you'll be able to download all of them when you get home. So first I have to acknowledge that I'm part of a much larger team at Red Hat, and I work in the performance engineering group. But there's dozens and dozens of folks that are already working on Docker and container technology and the orchestration level and management and all that stuff at Red Hat. So what I'm going to give you is a view of Docker from a performance analyst point of view. So I will eschew some of the security concerns for the time being. If there are, we take it very seriously, security. However, from a performance perspective, yeah. So, cool. So that's who I am. And this is what we'll talk about for, I don't even remember how long I have, but I tend to ramble, so someone tell me to shut up. We have, I'll cover what's interesting from a performance standpoint. Approach to performance analysis. I cannot do a performance talk without addressing the approach. Then I'll talk about some of the integration that we're working on into our performance regression tests, which are part of each product, that not just RHEL, but every product. Some of the interesting features of Docker that can get you performance boosts. I'll show you some test results, and I have a couple demos sprinkled in here and there. So, one more disclaimer. Docker is changing so fast, I don't think any one person can keep up with it. The ecosystem is growing at such a pace, I don't think one person can keep up with it. The analysts probably have the best shot. So, if you know a better way, a more streamlined way of doing something, feel free to let me know. I would like to learn that way as well. And so this is our approach, not necessarily the end-all, be-all approach to Docker. Just like anything in Linux, there's a guy with a Perl shirt over there. There's about 1,000 ways to do everything. OK, I came from an ops background in a data center management company. So we were doing essentially data center thermals, and it was, I would call not big data, but like small data at the time, where all the sensors in the data center were, we were processing that data and providing thermal feedback to the data center operators, and we were managing mail infrastructure. It was just, all the normal ops stuff from a Linux perspective. I then came to Red Hat 5 years ago. 5 years ago last week, I've done several summit presentations. In fact, I'm fairly new to Docker, just like everybody, which kind of makes it cool. Everyone's roughly at the same level. But my normal focus is financial industry. I do low latency networking and kernel bypass, kernel timers, whatever, all that sort of stuff. And now I'm on Docker. So why is Docker interesting? I probably should have reordered these. The main reason for me is because it's not virtualization. And because performance guys, although KVM is exceptionally performant as compared to other traditional virtualization technologies, there's still overhead involved, context switching overhead, memory copy overhead, that you just don't see with containers. And Aaron, if you were in the 101 earlier, Aaron mentioned, he quoted some rough numbers about overheads, and they're pretty much in line with what we're seeing, give or take. It's a lot less overhead than traditional virtualization. So it's also lightweight and very easy to use. And it's fast, roughly bare metal speed. I have some numbers to prove it. Okay, here's the basic slide. When I take a look at any system, doesn't have to be Linux, but I like to think about it as food groups: CPU, memory, disk, and network. Listed there are an abridged version of some of the benchmarks we've run in kind of loose categories. LinPack for CPU, that's a math benchmark. IOZone, everyone's familiar with that. NetPerf for networking. And they are all interrelated, of course, and you need all of them generally to succeed, and they all need to be tuned and in balance. So that's the general systems approach that we take. When a new product is given to us in the performance engineering team, we try and be as close to the developers as possible. Sometimes that's a problem because the code's not ready to be performance tested at the moment. It's ready to be functionally tested maybe. But so what we do is we test for limits. We definitely want to know overhead of various namespaces. We want to break things, definitely want to make sure we know the limits, and essentially when things break, that's the ceiling. Can we tune around that and get the ceiling a little bit higher? And I'll give you one example. I think it's in a later slide, but when you hook OVS into a Linux system and you start adding thousands of ports to it, there are several tuning options that you need to apply in order for any of that to work. So we recently discovered some ways to boost the number of Docker containers connected to an OVS bridge. And that's through experimentation and some of our helpful network developers. All of this study of the performance of Docker and any product we evaluate gets documented in the performance tuning guide on docs.redhat.com. And we also ship much of that tuning, less aggressive versions, but much of that tuning gets shipped with the base products through something called a TuneD profile, which I'll go over a little bit later. And finally, we've been finding new and interesting ways to adapt our existing tests to a Docker-friendly patterns. That includes volumes and introducing bridges and some different tuning that we didn't see before we started using containers. So I have two interns here who are with me today, and their job, since they got to Red Hat, was to containerize some of the test plans. And that's either one of them, John or Rob. Okay. And so this is some of the stuff we looked at. And what Aaron was going over was, he mentioned what I'm going to call some old Web 2.0 technologies like LAMP stacks, Nginx, Postgres, those type of software. Red Hat is taking that approach as well, because we have OpenShift, which is a platform as a service product which supports gazillion languages and backend databases. But we also have traditional application stacks that we need to take care of. And those stacks are what we've been looking at with an extra close eye, because we don't see that being addressed in the ecosystem. So we want to calculate overheads, and we're going to throw databases and business analytic applications. I cannot name these by name, just they're heavy apps. Everything OpenShift can run, of course. If you haven't seen OpenShift, go to openshift.com. There's free web hosting available there. And we're going to actually, one of our guys, who I don't see here, Alex Cross, is testing satellite with containers. And what I mean is, he's using Docker as a tool. It's a lightweight, I'm going to call it a lightweight VM. But it's an interesting technique because before we had to throw up thousands of VMs, which took X number of hardware resources in order to scale test some of our products. And now we can use significantly less hardware to scale test the same level. And finally, I can't go through a cloud presentation without saying OpenStack at least once, so there it is. Red Hat's involved with integration between those two products, as you can imagine. So, questions before we move on?
So one question I have is, when you're baselining your system, are you essentially changing your storage backends and then also your container engine, execution engine as well, collecting results and updating them as well?
Yes. The question was, do we make any changes to the Docker defaults when we're doing our performance analysis? And is that what you're asking?
Yeah. So
Execution driver is one thing you mentioned.
So I can see like BTRFS versus Eder.
Yeah. OK. So the actual back-end storage stuff we have tested. I don't have slides of it right now. Yeah. I do have plenty of dev mapper information for you today. So I can't go any further without saying Alex Larson and Mike Snitzer, who wrote the code, and I merely know the knobs. So, performance impacting features, dev mapper is coming up. OK. Here's volumes. Aaron talked about volumes earlier today. And what I find interesting about volumes from a performance perspective is that if you don't use a volume, you're stuck with the defaults that the storage engine chooses for you, and the file system that's underneath it. Block size, all that stuff, stripes. And what volumes can do for you is allow you to, again, as Aaron mentioned, choose specific storage that's tuned to your application. So you have an application that handles many, many small files. You're going to do significantly different tuning than if you had several, just larger files. There would be smaller block sizes on the file system or chunk sizes on the file system if you're processing smaller files. And you can't do really any of that customization with a copy on write file system. So that's where volumes come in. And in fact, no matter what copy on write file system you choose, there's enough overhead to make it very uninteresting for serious enterprise workloads. So we're recommending volumes pretty much everywhere. And anyone who's developed on AWS and is familiar with attaching EBS storage to their application knows this development model already. It's nothing new.
So that kind of answers my question. You're basically saying just don't use the copy-write backends.
It depends what your storage requirements are, your performance requirements are. For heavy I/O, the volumes are going to perform significantly better, and you'll see it immediately. So the test data that
When you say volume, it's a logical volume?
It's so this is volume in the Docker context. Whatever it is on the whatever it is exposed on the server, it could be LVM, it could be a partition with a file system on it. So whatever gets mounted into the host gets passed into the container with the volume option. Does that make sense? I don't do a lot of volumes from, which is storage containers. I haven't really gone into that myself. So if you have performance data or any comments about the pattern of using storage containers and volumes from, I'd be interested to hear that too. I have in here within 5% across several workloads, and that's a performance overhead of even volumes. And I hear people saying there's no overhead, but I haven't seen a no overhead type of workload. So we're throwing pretty heavy workloads at it, and maybe that's why, but even volumes have some cost associated with them. So there's work to be done there for sure. And again, this is all early code, plenty of low-hanging fruit remaining. The last question on here is if anyone is already using copy on write as their primary storage for containers or intends to, I just would request that you test it with and without. And your mileage may vary, of course. So here's a device mapper slide. Why do I want to use device mapper? It's upstream. Everyone who's ever used RHEL, every Fortune 500 company that we sell to, they all use Device Mapper. It's got mileage on it. It's got features. It's got support. It's got several of the maintainers that work for Red Hat, which is important when you are running your business on this technology. And the default, actually, I believe at this time for Docker Upstream is Btrfs. And you need to adjust your Docker, whether it's a systemd or on Ubuntu, whatever they use, your Docker command line to adjust the storage driver accordingly to use Device Mapper. So our tests are using Device Mapper, all of them, and we are passing volumes in most cases. Does anyone have experience with Device Mapper? It's pretty easy. There's really not much to it. And there are a lot of knobs, thanks to Alex and Mike. Here they are. I hope you guys can see. I tried to make them as big as I could, but I'm not really in love with this Reveal.js. But anyway, so these are the knobs that you can tune for your Device Mapper storage. When you create a new Device Mapper, when you first install Docker and you start it for the first time, it actually has a couple of defaults: 100 gigs across every container, and 10 gigs per container, all thinly allocated. That's the max. So one container can go to 10 gigs, and all of your containers together can only go to 100. So that's probably not enough for you guys. So there's knobs now to adjust those sizes, base size, also to adjust the file system. RHEL 7 uses XFS as our default file system. Upstream Docker uses ext4, and they're both fine. We have definitely found XFS to perform better, and that's why it's the default in RHEL 7. There are a couple more knobs here. So when you install Device Mapper, you get a loopback mounted Device Mapper device and ThinP volumes within that. ThinP meaning thin provisioned LVM volumes using the DM ThinP kernel module. And you can go directly to a disk, directly to an LVM device as well, and that's what DM data dev and DM metadata dev, that's what those directives do. So you can reduce the overhead of the Device Mapper by removing that loop layer, loopback device layer, and going straight to either LVM partitions, and I think you can even go to raw disks as well. So there's documentation on that forthcoming, let's just say that. And the block size option I had mentioned, you kind of want to match the average I/O size to the block size of the ThinP volume, get it as close as you can. And what I did was I looked at Drupal, WordPress, MediaWiki, a bunch of these like common open source CMS frameworks and things like that, and I took their source code and I just generated some histograms to tell me what the most common file sizes were. And it comes, 128K, 64K is kind of where those peaks in the histogram were. So block size of 64K, which is the default, is probably fine for everybody. But there's a knob in there in case you want to do larger IOs. You'll have less overhead if you increase your block size. There is one problem, and this is a Docker in general problem, not a Device Mapper problem. There's only one storage pool. So unless you use volumes, you're stuck with these options for every container. And that's why volumes are so important, because you will find you need faster storage, you need storage that's allocated in a different manner in terms of what file system's on it. Maybe you find a workload where ext4 kicks XFS's ass. I don't know. So you might want to change your file systems on a per container basis. Volumes are the way to do that at the moment. So those two guys, and plus everyone else at Red Hat, who are just geniuses, and much appreciated their help. So that's Device Mapper. Any questions?
So do I have to know ahead of time how many VMs I'm going to have and provisioning the Device Mapper to? Or is
Okay.
it something that's stretchable and
Yeah, once it's set, that's it. In order to, if you didn't allocate enough at the beginning, you then have to back up your containers or rebuild them on a new graph directory. Yeah, which is why I use 2 terabytes as my max size, because it's ThinP allocated. Doesn't matter, it's a fake number. And each container, I think I'm giving them 80 gigs.
okay, so you just saying pick a big number, but
pick a big number, but keep in mind the thin P is not new. SANs have had them for decades, and if you bet that you're not going to fill it, someone's probably going to fill it. So you do have to ultimately pay the piper, and that stuff has to get to disk at some point.
Fine. I mean, if someone is taking its space, then you can't put more containers on. But I think it would be bad if you provision not enough, and then you want to add more containers, and now you're kind of.
Yeah, and in fact, the multiple. Oh, sorry. Repeat the question. So what happens if you run out of space on your graph directory? I mentioned you'll have to do an export and a re-import into a new graph directory. You don't have to blow away your old storage. You just change Docker and point it to a new directory. So there's an easy rollback path there. But that's the current state of affairs. And multiple graph directories and some additional flexibility from a storage standpoint, it has to be something that's coming, although we don't have any patches in my back pocket like I did last time. And I should mention, I have to say Dan Walsh's name 3 times, and he comes in the room, I guess. But he's writing a lot of these patches. So that's the situation with the thin P right now. Yeah.
Basic question. So the underlying LVM can be expanded and shrunk, but this graph directory that you mentioned is defined at the time you are defining it.
Yeah, yeah. And you know what I noticed is that, and this shouldn't have come as a surprise, but when I made it 2 terabytes, it took a long time for Docker to start because it's doing a makefs. XFS is really fast at makefs. exe4 is really slow at makefs. So Docker takes a long time to start the first time. But I'm using XFS everywhere anyway, so things are generally quicker.
So because of this, should I then maybe think about ETRFS as a storage backend?
Yeah.
Would that be an advantage that ETRFS has? Or is that a
So I'll say this. ButterFS, I believe, is the default in Docker upstream right now. It's not the default in Red Hat's products at the moment, and it's because we don't quite have the level of confidence in ButterFS that we need to ship it as an enterprise product. And we definitely have the confidence in Device Mapper to that extent. So ButterFS, we still ship it. It's what's called what Red Hat calls technology preview, which means it's available but not supported. Yeah. So one of the things you'll see when I get to my Docker file is I install ButterFS progs because sometimes we're using it. So it's been tested, but we're going with Device Mapper and volumes at the moment, with plenty of development around that. That's a storage story. On to networks, my favorite thing. The major development for me was the addition of --net equals host, which exposes the host's networking stack directly into the container. What it does is it skips the new net namespace creation step. And so you see all the NICs that are in your system, which is awesome for performance, because actually the bridge does have plenty of a performance overhead, and I have plenty of data to back that. And anyone who's ever used a virtual machine on VMware or RHEL knows that there's an overhead with the bridge network versus bare metal. So our job was to quantify that, and we did. So from a performance standpoint, it's awesome. But it kind of does limit you to 1 container per physical machine unless you do some really funny gyrations with port allocation. You can't run 2 web servers unless they're on different ports, and then you have to worry about IP tables. Or run them on different ports since you only have 1 network stack to deal with. So --net equals host is awesome for performance, but has a very limited use case. It also helps us with some UDP fragmentation issue in the Linux kernel that is yet unaddressed, but you will see with network namespaces. So if you're trying to push any UDP packets larger than an MTU, you hit the kernel's UDP fragmentation code and splat, it goes to shit. And if you use --net equals host, that doesn't happen because the namespaces are not in play. The default networking setup of Docker is a bridge on a network that it picks, and that could easily overlap with another network on your another subnet on your network on that particular switch. And so for every test, we define our own bridge on our own IP range that we control, because Docker's IP allocation policy is, frankly, suboptimal. It will pick the lowest IP address in your subnet range and then just increment from there. And there are only some really hacky ways right now to get static IPs going. So for me, who I kind of like static IPs for my tests, it's kind of a kludge to get it all working. But that's why you kind of need to define your own bridge with their own networking configuration on it, because it will start allocating IPs that might overlap with your like prod gear or wherever. So it's kind of a little bit of a loaded gun there. And so if you're in dev and you're on this laptop here, like I've got the Docker 0 bridge, which is the default bridge that it creates, and everything works just fine because I don't have another 172, 117 network here. So that makes sense? So a couple of things that happen by default. Again, the thin P allocation, or the storage graph directory allocation, we'll say, whatever the back end is, and the bridge setup. Those are two things to keep in mind. The bridge itself is performant. All the KVM benchmarks that we publish, most of them anyway, use bridge. We have pass-through technology in KVM as well, just like every other traditional vert vendor. But the bridge is a performant technology, just not as performant as bare metal, and overheads kind of upset me. So I also get paid in buffalo wings, I should say. So for every percent of performance increase, I get a buffalo wing, and I actually don't get paid by Red Hat, so kind of like working here, and that explains the weight. Okay, C groups, which let me say one other thing. Docker makes it easy to use many of the existing technologies that Linux already had. RHEL, or Red Hat in general, we had this technology in Fedora for a while. It was called Vert Sandbox, Vert Sandbox. The reason Docker is interesting is because it's far more polished than that technology, and it's got industry momentum behind it. I happen to love it, but none of the underlying technologies are really that new. We've had C groups in RHEL 6 for several years, since November 2010 for sure. We had several other namespaces even in RHEL 5 CPU sets, so at least 2618 had CPU sets. Those are namespaces, and they've added them more and more over time. Docker likes to talk about 3.8. I don't know what namespace that refers to, but that's their baseline version. RHEL 7 is 3.10 plus a gazillion patches, and that's what we've been using for our performance testing. Anyway, the C groups on RHEL 7 are children of systemd, so we changed our init system in RHEL 7 over to systemd, which is a godsend because it is awesome. And provides us so much more flexibility than sysvinit. And it allows us to build the cloud, really. Honestly, if you ask my opinion, without systemd, we have a really big problem enabling the dynamic workload stuff that developers and customers have come to expect in a very short period of time. In earlier versions of Docker, up to 0.8, they used an LXC execution driver backend, which had, over time, grown many, many knobs. LXC never became part, the LXC tools package, which it relies on, never became part of RHEL, so, which was fine. But that means that there was a new backend developed called libcontainer around 0.9, and that's the default going forward. Unfortunately, there's a couple of things that libcontainer still can't do that LXC backend can do. So on Fedora, you can choose LXC, and you get a couple extra knobs, and I'm sure libcontainer will catch up rapidly.
Has libvirt not been added as a backend?
No.
So there is no plans to do that?
We originally had that plan. The question was, will you be able to manage containers with libvirt? And the answer is no. That idea was scrapped several months ago. So not happening. Okay. The libcontainer backend exposes several C group configuration knobs, CPU shares, which for me are essentially useless. But what that does is allow you to take, carve up your resources and give them proportional weights. If you have 10 containers and each one has 100 shares, the total is 1,000. Each one has 10% of the CPU. That's how CPU shares work. I have no idea how anyone applies that in reality, but that's how they supposedly work. It's a budget. And did you have something to add? Have you seen them in use?
They don't.
They don't. Yeah, no one does. Okay. So VMware's had that for like a decade, and I've never ever seen anyone use it. So anyway, the second one is CPU sets. That allows you to create a mask, a CPU mask that the threads within the container can only execute on those cores. And you may want a container to only run on the odd numbered cores because that's the one that's local to your NIC, PCI local to your network adapter, and so it's faster. That may be one of your use cases. Another one may be you want to have your container run only on certain memory banks because those memory banks are local with certain CPUs. Everyone is aware of the word NUMA? Yeah. Every piece of hardware ever. My phone is going to be NUMA next time I upgrade. And you need to be aware of that when you're performance tuning as well. When I did a talk at Summit, it was like 50% about NUMA, and it was a over 2-hour talk. So anyway, getting that right is important. What's great about RHEL 7 is that's Rick Van Riel and, oh gosh, I forget their names. So there are several developers upstream, not at Red Hat. Rick Van Riel is a Red Hatter who helped implement NUMA balancing in the kernel, which automatically keeps threads and their memory allocations, or tries to keep them on the same NUMA node for you automatically out of the box.
So when you are doing CPU set, are you getting memory affinity on the same NUMA node by default?
Yeah, in RHEL 7. Because of this. Because of the automatic NUMA balancing scheduler. In RHEL 6 and any kernel that doesn't have auto NUMA balancing, you get soft affinity. If the scheduler, well, the first time the task is created, it allocates its memory, and it will be allocated on the same node that the task first run on, but sometimes the task can move away from the memory. So people hand tune their systems. Anyone on Wall Street has a really complicated tuning setup, and having seen those setups, I can tell you they can get very complex. But the reason is because the performance is noticeably better. And those guys are competing on performance, so yeah.
Would there be a way to say, though, as part of the CPU search definition that I want to run my container on a certain socket?
You cannot do a socket, but you can do, if you know what the cores are, I'll show you. If you know what the cores are, you can create the CPU set mask to match a socket. And in fact, that's indirectly, but here's another cool thing. When you're inside the container, if anyone's familiar with NUMA control is an application that you prepend to your command line, and what it does is it allows you to set NUMA affinity for that task. And you can do minus N1, minus M1, and then it'll only run, N meaning the socket, it'll only run on socket 1 and memory bank 1. And you can do that in a container. And fun fact, before Docker exposed sysfs into each container, the containers had no clue about system topology. And then I think 0.11 came, and they decided to pass sysfs into it. So your container now knows the hardware topology, and the kernel can you can then programmatically decide what cores to run on because the topology information is exposed to you. I can show it to you.
Did you mention you did a talk on NUMA performance tuning?
Yeah, if you go to YouTube and search for my name, it'll be on there. We did several, and it's just, the reason auto NUMA balance was invented is because it's hard to get right and no one wants to hand tune. Let's just do the best we can, get 80% of that performance win out of the box, and that's what we have in RHEL 7. So, and that technology is constantly getting refined. Okay. Memory limits is another one, so you want to give your container 512 meg, and that's part of the demo right now. And then NS-init is another. It's shipped in the Docker source tree, or it's part of libcontainer. And what it does is it has several modes, but one of them allows you to dump statistics about your container. So per container statistics, and all it's really doing is reading the counters that cgroups already exposes. And another thing it can do is dump the container's configuration. One of the interesting, I got some screenshots and I uploaded a snapshot of it to GitHub because to build it is ridiculously hard. I have no idea why you have to build it the way you do, but I think I also put a binary on GitHub because it's such a pain in the ass to build. Anyway, I mentioned LXC backend. If you want to switch to that, it's -e LXC when you run Docker, and that's it. Libcontainer's catching up. Questions? This side of the room's light on questions. Okay. Now here's where I take some exception with Aaron's talk about portability between different operating systems. Different kernels have different capabilities and different performance characteristics. And so while the user space might be portable, the performance might not always be identical, because kernels are different. Different revs have different patches, have different default behavior. If you use 3.8, you get no automatic new balancing. If you use 3.10 plus something or other, you do get it. It'll be an entirely different performance. So, and also new features are added between different kernels. So I can't say that while it is portable from a packaging standpoint, you will see different characteristics wherever you run it. If you run it on Amazon or Tutum, whatever, there will be different performance characteristics to your application. So I'd like to say that RHEL probably has, in my opinion, the very best kernel there is, because I worked on it, and that's why I have no hair left. So we've been working on container-like technology for many years with OpenShift, and kind of before kernel Linux namespace containers were really ready, the team, Matt Hickson team, built OpenShift on RHEL 6-based technology with their own homebrewed stuff, and we did lots of scaling work for them. And we learned a lot in the process. And actually, a lot of it translates right over to Docker, because there's not a lot different about Docker except the packaging and the ease of use, at least between OpenShift's backend. And I just, that's the understatement of the year. But anyway, so we learned a lot of things about tuning SE Linux and kind of maximum number of files open, because we were going really, really dense, many, many thousands of containers and applications running, and JVMs have a shit ton of threads, so you have to bump max PIDs if you're trying to go really dense. Open files depending on what your application's I/O patterns look like. We also bumped into some limits with NetFilter, and I had mentioned earlier about OVS, about Open vSwitch. And what happens is when you add a port to it, it sends an ARP request, and every port answers. So if you have 1,000 ports, every time you add a port, you get 1,000 ARP replies. That's 1,000 packets through the kernel. And the way that this is Jiri Bank who root caused this for us. The way that you mitigate that, step back. The kernel puts it on a queue and set and forget. It doesn't worry about retries. It's ARP. It's not TCP where it might have any type of recovery in it. And if you go over 1,000, those packets end up getting dropped. So the ARP replies never come back. And the way to deal with that is to bump up netdev max backlog. Now, all of this stuff is not really stuff I want you guys to ever have to deal with. This is our job to worry about. And that's where one of the upsides of RHEL is that we ship all that stuff. We ship all those knobs, or in this case, we're going to ship those knobs to you in the future. And you'll be able to get way more dense and not have to do any of this awful grunt work. And your systems will just hum right along. So, can't I just push a button? Where's my easy button? I hope this is an easy button for you. It's called TuneD. How many people have ever heard of TuneD? Put your hand down if you've worked for Red Hat. TuneD is my baby. TuneD is my baby before I started working on Docker. And what TuneD is a tuning profile delivery mechanism. So the kernel has defaults, and those defaults do not work for every workload. The kernel has auto-tuning in certain cases. Socket buffer sizes is one of them. What's the other one? Read ahead is another sort of kind of auto-tuning. And in reality, there's a lot of stuff that isn't auto-tuned, and you need to make your configuration changes based on your experience. So what we did was we delivered a handful of profiles that we attempt to put workloads into a box and say this is a storage I/O intensive workload, or this is a latency intensive workload. And we have groups of settings that push performance, push the needle a little bit, and we usually try and keep it 10 or 15% over baseline before we introduce these knobs. And you can certainly get more aggressive than we are willing to do. But that's what TuneD is. So if you have, and the reason I mentioned throughput and latency is because those are directly opposed to each other. If you're tuning for throughput, you're going to get crappy latency. If you're tuning latency, you tend to reduce throughput. Will, who works on performance tools, helps me with all that stuff, Will Cohen, and helps me debug all kinds of fun stuff. So We ship profiles, and hopefully one of your workloads fits into this box. If not, you can create your own and use our delivery mechanism, create your own profile. There's a concept of inheritance, like an Apache include. And you can take our profiles, and in RHEL 7, the default is throughput performance, and it's 10, depending on the workload, 10, let's call it 10% over baseline Linux kernel. So if you take boot to Docker, it's going to be untuned. If you take, I'm not even going to name other OSs. If you take other OSs and you don't apply any tuning, RHEL, and given a roughly similar kernel baseline, we should have better performance because of tuned.
You're just adjusting sys controls?
Mostly. There's also power management in there, depending on the profile. There's memory management tuning. One of them kills transparent huge pages. So it's more than just sys controls.
Turning off transparent huge pages?
In one of the profiles, yeah, for latency. Because
Are you changing the profile of the entire system, or just you're able to tune it on a product?
unfortunately, the tuned stuff, well, you only have one kernel. And not everything is namespace aware. If you search on GitHub issues on Docker, you'll see 4227 or something like that, the pull request for, or that's an issue, not a pull request, for per container tuning. But you'll never be able to get per container tuning like you could in a VM because you have one kernel.
Unless you make everything in the kernel namespace aware.
Yeah. So I'll be dead and buried by then. If these bugs haven't killed me first. So anyway, the concept of inheritance is what I wanted to get over to. And the green ones are what you guys invent. They could be blank. They could have some magic knob that you don't want to tell anybody about, but really boost your performance and you win all those trades. And you can use this method to deploy. Anyway, this is all in RHEL 7, and it's in RHEL 6. It's not in RHEL 5, unfortunately. We had a nascent version in RHEL 5 called Ktune. OK, it's come a long way. It's in basically every product that Red Hat sells at this point. Yeah, RHEL 6 and 7, Rev, OpenStack. We don't have a satellite one at the moment, but we do have numbers that suggest the default RHEL 7 profile boosts satellite performance quite a bit. And of course, we've got Atomic in there, which comprises, so how many people have heard of RHEL Atomic or Project Atomic? The purpose of that operating system is to host containers. It's a thin OS for hosting containers. And some of the tuning I mentioned earlier about SE Linux and syscontrols and NetFilter will roll up into those profiles eventually.
What makes it thinner than a base RHEL install?
You could build the same list of packages with a well-crafted kickstart. RHEL Atomic has one other different thing. You actually can't use Yum or RPM to install stuff on RHEL Atomic. It is Atomic. And to update it, you type Atomic update or upgrade. It pulls down a Git tree and changes the bootloader, and you reboot. That's it. So to install packages on Atomic systems, you don't install packages on Atomic systems. You install containers on Atomic systems. And those containers contain whatever.
So how is this different from the core OS based?
I'm not a marketing guy. I'm so sorry. The question was, how does it differ from Core OS? I really shouldn't even comment on that. I can say that Atomic is awesome. You should try it.
You get the answer.
Oh, and oh shit, that's the wrong, well, that's one of the links. There should have been another link on here. How to create your own profile is on the Red Hat portal. If you're a Red Hat customer, I think it's behind a paywall. Apologies in advance. But there's another one who I'll fish out the link for it, and it's how to choose a tuned profile. And what it is like any benchmark that we ran that boosts performance, we say, okay, Sybase needs this profile, or Oracle needs that one, to help you choose which profile if you didn't understand your workload well enough, confidently enough.
So is it a script? The profile is in short a script that is executed?
It's a key value file. It's more than a script, and it's actually more than the key value file. But I can show it to you. If we have time at the end, I'll show you the guts of it. I can talk for about over an hour on just tuned. It's because I told you it's my baby. So this is what some of those tunings can do. And we went to like 3,800 containers on on RHEL. And at that time, this is right after SE Linux support. And at that time, we found that each container getting a new MCS label. If you're not familiar with MCS labels, I'm not either, so I can't help you. But each one of them added some overhead to the system, and to the point where we were actually going to disk to fish out some SE Linux information instead of everything should happen out of RAM, and at least as far as the kernel goes. Anyway, the cache, there's a cache. sys, fs, SE Linux, AVC, cache threshold. It's set to 512 entries, and I have no clue why it's so low, but it is. And what I did was I started 3,800 containers, and with the default tuning, it took 25 minutes to start all that, which is insane. And then I ran perf. Who's familiar with perf? If you haven't used perf, perf is like the thing, right? And when I say the thing, I mean if you're trying to do analysis of any bottlenecks, perf will give you the answer like that, right? Perf is a utility that uses hardware counters and kernel trace points to summarize what your CPUs are doing at any given moment. It uses sampling, but gives you most of the picture in an instant. I can show you perf in a minute. Basically, when I saw this system was grinding like 25 minutes to start all those containers, it's insane. First thing I do, perf top, tells me it's an SE Linux bottleneck. Go to the kernel source, find out where the knobs are, talk to Dan Walsh, and magically find these knobs. And look, we went from 25 minutes to like 5. So that's a knob that if you're not using RHEL, you'd have to have found on your own. And again, you'd be as bald as me after trying to dig this stuff up. Because everyone else who's shipping a Linux kernel, this is 4096, it's actually 512. It's somewhere over here. God knows how long that would have taken. And we're here, 64K. Because that's kind of where law of diminishing returns. No reason to set it any bigger. OK. So I mentioned NS init earlier. Oh, wait a minute. Shit. You guys, I totally forgot a demo. OK, I'll come back to it. I'll come back to it, I promise. I'll do both at the same time. OK, so here's the performance monitoring and slide, because this is kind of what all of our jobs are about. And there's over 20 of us in performance engineering at Red Hat. One of the few groups of our size in the open source space that does performance analysis on open source software. And in collaboration with, deep collaboration, I should say, with Will Cohen's performance tools team and several of the other kernel teams, they have worked to add new and fun knobs to the operating system and supporting monitoring utilities like Performance Copilot in RHEL 7. If you haven't heard of that, it's pretty damn slick. And sysstat, which is everyone's favorite, vmstat, iostat, ampstat, all those packages come from upstream sysstat package. Those are system-wide. But what if we want per container? That's where this NSInit magical program comes from. That's a Michael Crosby special. I don't think it belongs, if you ask my opinion, which you didn't, I'll give you it anyway, it should be Docker. Jesus. Sorry, sorry. Anyway, that new net wouldn't be in there because that's a networking namespace. Those are the namespaces that are in effect for this kernel at this moment. And you can imagine how fun this is and useful this is for debugging. And here's the list of capabilities. What Docker does is when it starts, it drops a whole bunch of capabilities by default. And it keeps the bare minimum. So all of them get dropped. Thank you very much. And the only option you had up until very recently was to add all of them back by creating what's called a privileged container. And it's basically root on the host, and it bypasses a lot of SE Linux as well. So recently we added the ability to enable and disable capabilities on a per capability basis. --add cap, cap add, I think it ended up being. There's a whole debate about that. But anyway, so here's what's in place on the Docker container at the moment. And then it'll also tell you what kind of networks are connected to it, tell you the C group information, and finally, this is the SE Linux context of it as well. Restrict sys is whether or not this container is privileged or not. Restrict sys actually doesn't turn to false, it actually just disappears if it's a privileged container.
About NSM, you were mentioning there were like difficulty to build it. Apparently, since like last week, there's a Docker file from the container repo, so all you need to do is just go get github.com/docker/container, and it should be all.
But that was building in, did that do a from Ubuntu?
I have to double check, but did that do it from Ubuntu?
So the way
But it'll output the same binary either way.
right, I'm not able to use Ubuntu VMs to build technology for our customers. So
It might be used as
that's cool. I hope it just gets built and shipped, you know, like a normal package rather than, anyway. Okay, so this is kind of the meat of the presentation, which is the test integration. What we're doing is, and my screen stopped mirroring, but and that is way too small for me to read. Is anyone having problems reading this? You good? My eyes are shot. I think I said I'm old. So anyway, we created a container. We're calling it the perf container, the perf debug container, and it's got everything in it that we could ever want for debugging performance problems, whether that's sysstat or perf or system tap or all that stuff gets sucked in there. And plus other useful utilities like IP and PS. I use containers as machine containers. Aaron alluded to a machine container or an app container. All the containers and stuff that I'm talking about, I'm using them as machines because I need to do debugging on them, low-level debugging. The only way to do that is to get inside the container or be on the host and monitor what the kernel's doing. So that's why we created this container. And the Docker file I used to create this container is up on GitHub right now. I'm using CentOS 7. Obviously, that's not what I use internally, but that at least is free, and Docker pull CentOS, done. So set up the environment. That sucks in our bash RC and our team Git repositories, which includes all the tests and benchmarks and all that stuff. And we developed all of this with Git in mind. It's a Git-driven workflow where everything has to get into that Git repository because the first thing the Docker file does is pull that Git repo, clone it. Everything's in the container. I can install any benchmark I want, and I can run any benchmark I want. So Git is the new hotness, 10-year-old hotness. And like I said, we're using volumes everywhere. Is there a question?
So you have RHEL-based host. Do you expect that the performance will also get a boost if you have actually the base built in the Docker container also RHEL-based?
I would say this. We have maintainers for all of our user space packages. And they usually are upstream contributors, or almost always upstream contributors. We have folks that work on glibc, GCC, Python, all that stuff. So we hope our products are the best, even though they may not be the absolute most cutting edge. They're stable, and they should be performant. So in that way, I would say that RHEL containers on RHEL will probably work best. Yeah, just because I have the most confidence in our packaging and our developers. That's
Probably would do more testing on that environment.
yeah. We definitely test. I mean, yeah, with that. So the only other image that we use is BusyBox, and that's like a sanity check image type thing. Besides the rel images. And then the last thing I should mention is that the mount situation, the volume situation, we're going to be using those volumes to, any storage I/O type of benchmark is going to be writing to volumes because it's so much faster. I mean, we did basic, not even basic, we did extensive debugging and performance analysis of copy on write. And we found that the overhead would not suit a lot of these very heavy workloads. So that's when we switched over to volumes. I like to make the EC2 analogy because developers should be very familiar with this storage that either stateless application development is basically what I'm saying.
You mentioned there is still some overhead with volumes?
Well, it seems that way. And what I mean is like a handful of percent. Yeah, so low. And you'd really have to be looking for it to see it. Yeah. So we ran some very heavy, like I said, database and business analytics type workloads on them that are very difficult to do good at even on bare metal. You need really serious SANs and huge amounts of memory and cores to make them go. And volumes were the only way we got really, well, first of all, the results were far more deterministic using volumes. And they were, again, in the low handful percent off of bare metal. So that's what we're seeing. OK, so here's the way the test flow works. At your host, I build a container which sucks in the Git repository. I have a container now with a Git repository in it, and a volume will be exposed to it. I forgot to add the Docker, the -v to the run line, but it's supposed to be there. And that's the benchmark that gets run. So this is not a machine container like I'm using for debugging. This is, well, let's call it an application container because it's only running this script, which does a whole bunch of gyrations inside it. And then the data gets output. In this case, it gets output to a flat file. So let's see if this demo works out or not. Everyone able to see that? Was that a yes? We're good? Thanks. OK. So this is a RHEL 7 VM running on my laptop. So it's going to be the slowest thing. It's just not going to be performant. But this is a functional type of test. So I just want to show you how we run these benchmarks. We can run these benchmarks in such a way that they're inside a container, but yet the result data gets persisted. The Docker performance, so it's github/myname/Docker performance if you want to clone it. And I assume, oh, they're in the slides. It's in the slides as well. So you can clone that and suck down all the data that I'm going to show you. So I really wish I could see this on my screen, but I have so I already built the Docker file because I wasn't sure about the networking situation in this room. I'll show you the Docker file. So I already built this, but basically it's as simple as it gets. And by the way, when I first saw these things, I'm like, oh my God, someone's reinventing Kickstart or Jumpstart. And that's kind of what it is. But it's far less featureful than any of those. And in a way, it's novel because it's so basic that anyone can do these things. And really, all it's going to do is run yum a couple of times, some git clones. I like my environment the way I like my environment set up like Unix has been for the last 100 million years, rather than some blank env, which is insane. And env container Docker was NAC'd upstream, so we're setting it, and the scripts use that to conditionalize their operation. So that's all the Docker file does. So it sucks down, like it says there, from CentOS 7. It pulls down the CentOS 7 image. It runs these commands, and it spits out a container called C7perf, because that's what I named it when I did the Docker build. I gave it a tag called C7 Perf. Okay, here's my run command line. And time doesn't necessarily need to be there, but how many people are familiar enough with the Docker command line? So I'll skip. I mean, I'll run through it, but I don't want to go into too much detail. I want a terminal. I want a volume mounted /results. I want a CPU set, which means I only want to run on core 1. This laptop is so old, it only has 2 cores, which is only half of what my S5 has, phone. And it's going to limit it to 1 gig of memory. Before I do that, I want to show you that the results directory on my host system exists, but it's not labeled properly. So I'm going to label it properly. And what that did is it opened it up. SE-Linux put a SE-Linux label on it that allows any container to read it. Any container. So in a shared environment, this would not be what you want to do. We have, again, patches pending to make this all automatic. And there's some debate about what the command line is going to look like, which is why they're not there yet. So in the meantime, you got to run something like this. I could. It'll run behind the bridge. This is actually not going to be a network test. This is sysbench. It'll be a CPU. The idea is not to really the results of the benchmark. It's the process. So anyway, I've got the SE-Linux stuff set up properly, and I'm going to do Docker run. And if the demo gods are with me, I'm inside the container. So I see I have my RHEL 7 kernel. The tool free reads from proc and tells me I have 2 gigs of memory and 1 gig of swap. And LSCPU is not namespace aware and is not C group aware, so it shows you both cores. Do you see the last line on there says 0, 1? So this laptop has 2 cores. Even though I told it it can only ever run on core 1, LSCPU, the LSCPU command, like I said, not namespace aware, shows you the whole system. There's a lot of utilities like that, even top. So top will only show you my process tree. There's a PID namespace, so I only see my processes. In this case, there's not even an init system. Bash is it, and then top. But if you look up at the top, actually this is different on Fedora, so I apologize. But you can see all of the system-wide information there. Yep. OK. Now, so that was a container. This is one of these C7 perf containers. All right, so stupid easy. Instead of running bash, I'm going to run this script that was pulled down as part of the Git repository when I did the Docker build. It did a Git clone. So this is what I just showed you with bash is what Aaron was calling a machine container, and this will be an application container, I guess, by that definition. My script takes a couple of options. Sysbench has several different operating modes. It's not important. I'm going to do a CPU test, which calculates prime numbers. I'm just going to give it a tag of test1. So the script does a bunch of things. The first thing it does is see how it says running in a container? That it reads out of the environment variables from my Docker file. It creates a couple of directories because I'm eventually going to run, not tonight, but I could run an OLTP workload on here using sysbench. Sysbench wasn't installed in my container, so it's installing it, and now it's running the benchmark 10 times. And this usually takes about 30 seconds. It will spit out a histogram of all 10 benchmark runs. So while this is running, any other questions, comments, flames?
Measuring the performance of workloads inside a container. Have you also looked at the performance of just Docker itself? In terms of like, if I do a Docker diff, then with different storage backends.
Yeah, diff. We haven't tested diff. We haven't performance tested diff. Yeah, there's pull is. Pull is one that we've tried to look at and optimize. I think the major optimization point for pull was reducing the image size. And there was a lot of work done there to factor, because there's years worth of dependencies between packages. And one of the things that we needed to strip out, which I think Stephen Tweedy did, was, or at least he certainly focused on it, was stripping out locale information. Because if you look at user share, it's massive. There's like no reason to have that in a purpose-built container. Locale information. So that was one thing that took the image size down significantly. And the RHEL 7 image right now, which is only available to, it's in like a closed beta thing, it's like 52 megs. But like I said, it doesn't even have IP or PS. So if you're going to use it as a machine container, you got to add a lot more stuff, which is kind of where this C7 perf container came from. You might never have use for any of those, to install any of those. So they're not included in the RHEL 7 image, and it's really pared down. So get a Docker pull takes a very little period of time. I expect things like, let's call them a little bit more advanced layering operations. There'll be some performance analysis on that, perhaps by my team. I don't know yet. Yeah, or the team I'm on, not my team. OK, so it ran in 38 seconds. And I should, yeah. So since results was passed through as a mount, I'm on the host right now. And I see the data that was output by that container. There's a raw log file and then a post-processed log file, which is the histogram. The pre-processed one has a lot of data that really shouldn't be that interesting to us right now. So I'm just going to do cat star histogram. And you can see here that, let's see, to do 2, 5, 6, 7, 8. 8 out of the 10 runs are really tight, and there's a couple of outliers. And that's generally what you'll see with performance. There'll be a couple of outliers. That could have been a scheduling delay. It could have been some other task got scheduled on that core, and this guy got moved to another one, so a migration. Point being, or could have been a kernel timer tick, anything. But the point being that not necessarily that sysbench ran in 3 seconds to calculate prime up to number 4,000. It is the methodology. That run sysbench script could have been anything you guys want. Any regression test, any functional test, and the git clones could be anything that you're using as well. So this should be really generic and run sysbench, swap it out for anything. So only sysbench is pushed to the Docker performance GitHub just for the sake of the demonstration tonight. But as you can imagine, there's a gazillion more of them. And whatever you guys are currently using, slap it in there, use the same framework and slap it in there. I think that the key thing is that if you don't use a volume mount, that you find a way to get that data off the container before in your run script. You SCP it off, or FTP, whatever you got to do. Because once you stop that container, although you can start it again, it's kind of an unnecessary step to have to do that. And some people start containers with --rm so that they're whacked at the end anyway, by default. So does that sound sane? Is anyone already doing that? This stuff? Well, like I said, there's probably 1,000 ways to skin this cat. This is the one we've chosen because it's centered around Git, which is a natural thing for Docker to deal with and for container workflows. All right. The next demo that I skipped earlier was about C groups. And so I'll run bash. So I've got my shell. I don't have my aliases in here. But anyway, I've got my shell. And you guys saw there's a 1 gig memory limit on this guy. And so what I'm going to do is run a little utility that's called stress, which is in Fedora, not in RHEL. I'm doing this from my m1 minus vm bytes equals 1g. So this is just going to take one worker thread, one memory allocation thread, and allocate 1 gig of memory. That's it. So it's an artificial workload generator. And I didn't guess right. Here we go. OK. So it's going to allocate 1 gig of memory. And remember, this is on a terrible, terrible laptop. So it takes a while. On a decent server, this should be a second or less. And It's also running in a container, and what I mean is it's got a memory limit that it's bumping up against because I've only allocated 1 gig of memory for the VM. So this is bumping up against the limit of that. And eventually it will complete. Questions while that's running?
Is it shift movement to Docker eventually?
Yeah.
Are they running into some surprises, or is it?
Every day is an adventure, man. I'm not on the OpenShift team, but I do work indirectly with them. And we've announced publicly that we're supporting Docker like full force. So, and we also did a press release about Kubernetes support. I don't know the technical details of that integration. So, but the short answer is yeah. Now this thing may end at some point. I mean, good night. I definitely didn't take this long when I tried it. Let's try a little bit less. Let's try, just to show you it completes, 20 megs. This test is not a performance test. This is a test for whether this is a functional test for C groups. So the answer to your question is yes. Everything gets run on bare metal.
And do you see like a big hit from just the namespaces part of
No.
data?
Nope. Nope. You don't see a big hit.
Have you tried Docker in Docker?
No. That's unnatural. We need holy water. Anyway, so it completed in 5 seconds. Aaron mentioned Docker and KVM and Docker and like its inception, which is the name of Chris's team, I guess.
That's how Google runs.
It's awesome.
I mean,
I love it.
Google runs VM. They run the container, and then they run the VM. And then sometimes they'll, like Appen just runs the container inside the VM.
Yeah, so maybe there's lots of interesting things going on.
I don't know what they're doing.
So this allocated the memory. The reason I wanted to show you this benchmark was, or not this benchmark, this workload, was just to show you that that C groups are actually in effect. So I just tried to grab 4 gigs of RAM and it exited immediately. Because I can't allocate 4 gigs of RAM because I don't have 4 gigs of RAM. But what happens if I do 2G? Now, the other one took a really long time, so I hope this doesn't take as long. But I actually have 2 gigs because I get a gig of swap by default. And so technically, the system sees 2 gigs of available memory, even though one piece is actually backed by disk. Can anyone guess what just happened? Killed it because the system has, this laptop only has 6 gigs of physical memory, but the container, as you saw when I started it, I did a memory limit of 2 gigs. I just tried to allocate 2 gigs of RAM. Every bit of RAM was full. The kill comes in and kills that process. Now, if I look back on the, I promised to make this bigger. Okay. Well, if you haven't seen kills before, they log a whole ton of stuff to demessage, and I promise you that is the tail of the kill. It actually says it. And it tells you it was stress. So, point being that the C group stuff actually works. And in the memory C group anyway. So we've done these functional tests on all the different subsystems. No, the kernel has an kill function. Means out of memory, sorry. Yeah. So it's like it's talking about killing and sacrificing children. I mean, it's almost like they're running Docker in Docker. So that is the second demo that I missed earlier, and I have to thank the demo gods. Both of them worked. Okay, so it's 8:20, and I've been talking for a while now, and I've heard several really awesome questions. The one really cool thing that I wanted to mention, I kind of mentioned earlier, one of our performance engineers testing satellite with containers. Several years ago, we were looking for a way to put like 10,000 VMs on Rev, which is Red Hat Enterprise Virtualization, or let's call it a VMware equivalent. Marketing people just rolled over in their graves. So We were trying to put a ton of VMs on there, and the KVM guys actually had to invent something because the regular KVM stuff was too heavy. You would need a ton of hardware, like the minimum amount of memory would be 256 megs or whatever it was to boot a RHEL kernel, and we just could never get to 10,000 without a serious amount of hardware. So they invented us a little shim that pretended to be a VM. It's called FAQEMU, F-A-Q-E-M-U. And it turns out that the containers are even lighter than that. So Alex came up with this on his own, and he's got satellite load testing, subscription manager load testing on against satellite using Docker containers. So what you could potentially do is load test your website, because each container gets its own IP. Funky stuff with the way SNAT and DNAT works inside IP tables with what IP address gets presented to the Nginx or Apache on the other side. But you could potentially use those as unique website clients inside Docker containers that drive load in one way or another. So that's the challenge, was to get to, how do we get to 10,000? You know, I mentioned 3,800 as a number where we're kind of, as of this week, and we'll do better. But that's the type of scale testing that Red Hat's doing across our product lines. So, and actually that's the best, that's the most fun part of the job. We're hiring. And we think that these containers can ultimately replace those older technologies, but the problem is that RHEL 5 and RHEL 6 kind of support is spotty, so we're not sure how widespread it'll be in the coming months, but longer term. Longer term. Okay, this is a performance talk, so I cannot, with good conscience, leave without showing at least one or two graphs. And these are where the buffalo wings come in. So the this is the OLTP workload benchmark I mentioned, the sysbench in OLTP mode on a Sandy bridge, which is a 16-core hyperthreading disabled. There is some tuning done on this system to help to, stabilize the results from run to run.
Why disable hyperthreading?
Because that's, so depending on the workload, hyperthreading can help or hurt. And I told you I came from like the financial stuff, and we never use hyperthreading there. So it's just always, it's never been something ever turned on my systems. So since I ran these, that's what it looks like. If you ask someone else on my team who does vert, they're definitely going to have hyperthreading enabled. So anyway, that's the situation. 16 cores. So this column, the 32 column, I ran that because it's an overcommit. There's more threads than cores, and that adds all kinds of scheduling overhead to the Linux kernel. And instances is, again, number of worker threads. The red line is bare metal. The blue line is Docker. You can see how close they are. The secondary y-axis, which is the one under my hand right now, tells you how many % off it is of bare metal, corresponding to the yellow line. So we're somewhere between 1 and 3.5% versus bare metal. So when I say low single digits, that's what I'm talking about. And these benchmarks are run for 300 seconds at a time, 10 iterations, averages, histograms, no shortcuts. That's how they get run, because we need to be able to make business decisions off of this data. So we can't cheat. Why didn't my graph show up? Shoot. Cyclic test is a kernel timer test. There should have been a picture here. I blame slides.com. And OK, so here's a networking one. So here's the proof of the bridge overhead right here. And like this is what I'm really familiar with, which is the low latency network tuning. So all of this stuff is done properly. I also wrote a paper on low latency network tuning for RHEL 6. I'll write another one for RHEL 7. But anyway, I came from that space. And so this stuff is like that particular case of customers is going to disregard these configurations, the bottom three, because they're sort of they're too slow. But your general web user, this is like invisible. So that's why I'm saying the bridge is really a performant technology. It's just not the most performant technology.
So percentage-wise, is like a 20%, 15%?
Yeah, but I mean, net numbers, yes, but in terms of microseconds, it's like 5 or 7.
Did you compare between Rage and OVS?
Yeah, we did. We did prepare.
Did you see a lot of difference between them?
It really depends on how OVS is set up, what kind of network cards you have. and what kernel version you're on, because that stuff is so in flight right now. And my coworker couldn't make it tonight, works on OVS, like it's most of his job, and he would have all of that information. So he ran those tests. I don't have them here. But rest assured that if we saw something that was crazy out of whack, we'd get our guys to help us with it.
Second question is the bridge performance. Would you vary the packet sizes?
Yeah. Well, okay. So in the latency test, it's one packet, so it's ping pong. User space on one side, reflect off user space on the other side, time it. How many times a second can you do that? Then divide by 1,000,000 to get the number of microseconds. So there's a little bit of math behind these slides, but basically this is one-way latency. So it takes 14 microseconds for a TCP packet to get from one user space to the other user space.
So what's the topology like? Is it the
It's like a Cisco 10 gig switch.
so there's a switch in between?
Yeah.
And when you don't have the bridge, you're just passing through the physical port.
When I don't have the bridge, you mean the container pass-through?
Yeah.
That's double-net equals host. So that's the most performant of the containerized networks. As you can see, these are sorted by order of performance. So host-to-host tuned is like when I get really aggressive with power management and some, really just the tuned profile for network latency in RHEL 7. And host-to-host, untuned, you can see there's a little bit more overhead there, and certainly more jitter, which didn't show up on this graph really. Anyway, the third one down is the best I can do, container to container right now. One way is like somewhere between 10 and 12 microseconds with the net host. And like I said, there's trade-offs for net host with TCP ports and stuff. Container to container with a bridge is actually the least performant. So anyway.
Pass-through is the host node, is that correct?
Yeah.
The pass-through, container to pass-through.
Exactly. Yeah. And it's all on the same gear, same NIC, same port, same system. On the throughput side, this is where I am varying the packet sizes. So the x-axis is packets from 8 all the way up to 64K. 64K is the maximum size that generic receive offload will batch its packets to. So anything larger is going to get chunked, and 64K is a really good logical stopping point based on current network card technology. And you can see, I should probably explain, the different colors are different configurations. This is TCP speed on a 10 gig NIC. And container to container within the same, container to container, then container to container with net equals host. You can see here there's like almost no difference. And that's because throughput type workloads like this one really don't hit the same bottlenecks as latency tests.
But how many containers do you have?
In this case,
Yes.
just one.
Just one.
Well, there's two containers actually. One container on two different systems, which by the way is a nightmare. Right now you got to use like pipe work to get the IPs lined up properly because it doesn't allocate IPs in any sane way, Docker. So I start Docker and it gives me .4 at the end of my IP address range. Next time I start at .5, it's not predictable. So what I do is I start my containers with --net equals none, no network namespace, and then I use pipe work to put in an interface with an IP address that I control. That's how the two host tests were done.
Would you limit the number of cores or do any of the memory tuning?
So these containers have full access to the hardware. So you can get, now this is just a receive. The 10 gig transmit looks similar. The lines are like right on top of each other. Okay, and then if you're familiar with LinPack, probably not, but it's a math benchmark is how fast the CPU can do several calculations, which I am not well versed in. But I can tell you that the pairs of lines, there are actually 4 lines on this graph, and the Docker lines are essentially on top of each other except for the 4 instance count. And there was a little bit of run-to-run variation. So I expect that's actually a lot closer, and even still that's within 5%. But run-to-run, that had a little bit of variation, which is fishy because LinPack usually is pretty stable. And then databases. An OLTP workload. The reason there's 4 lines here is because I did tests, not me, Sanjay Rao did tests that are with huge pages and then without huge pages in a container on bare metal. And so the pairs of lines are showing that the container has basically almost no overhead. It's within a couple of percent. Really encouraging for folks that run on really heavy applications inside containers. Okay. What other type of workloads do you guys want to run in containers?
Really CPU intensive.
Yeah. Well, there's a great story there. There's like almost no overhead. How about storage workloads? Anyone? Okay. Not me, but yeah. And AIM, and like there's a ton of them. I only showed a couple here tonight because at the end, I mean, this kind of stuff is interesting for me, but I'm just not sure if I can keep you guys awake. At the end of my deck, it's like those graphs suck.
Message broker like Cupid.
Yeah, we have a messaging workload. It's not Cupid, but it's messages. It's a financial benchmark that does messaging, and we've run that in containers, and there's nothing worried about. We're not worried about it at all. So if you have tolerances in like the single-digit microsecond range, you're probably not going to use any of this stuff anyway. So although Aaron mentioned financial guys are interested, it's probably more for the packaging than the performance. But the message broker workload we actually did for OpenShift 2 years ago. We did Cupid on EC2, and we had great numbers there too. Not with Docker, but with older generation containers. So the only thing that is like a major, not major, the only thing that's like something you should be concerned about is where you actually do your I/O. At the moment, you know, I'm being told, and the test results confirm that you should look at volumes, or at least do the volumes from another container. And then in summary, a couple other discoveries: ODirect, huge pages, NUMA, PCI, all that stuff still matters because you only have one kernel and you have no virt to deal with. So all of those numbers there are boosts that you would also see on bare metal. They work the same in containers.
So do you see anything there, any testing you would do on just a host process directly as opposed to doing that with a container? Is there anything degradation by there for running things in container?
Yeah, so the question was, do you see any workloads that regress versus bare metal? The copy on write file systems have overhead.
So essentially just the operations, because you were doing it with volume, it was not actually copy, right? So you've done those kind of tests just to see
Yeah. Yeah.
what kind of degradation do you see?
Double-digit percent. Enough that it's pretty easy to see. But like you have to put load on it. You know, if you got a guy checking email, you're not going to see it. But if you got guys pushing and pulling files like a ton of load, you'll see it versus bare metal on a copy on write. So file system aging is another test that we need to get to, because over time we don't exactly know the behavior of copy on write file systems that are very old. And it's not necessarily the per container copy on write, it's the global graph directory copy on write that's kind of the question at the moment. So right now we have these file systems that live a day, 2-3 days, a week for everyone to get their tests done. The global graph directory containers last for each test. But the file system aging is a test that our QE department already does on bare metal, and we need to extend that to container thin-p. So here we are. Questions?
When is Red Hat going to buy Docker?
I don't know. I have no idea, man. Listen, these things come as a surprise to me. I see the press release and hit retweet. That's what I do. So I don't know anything about that. Sorry. I have to say it's been a really fun project. I hope you guys find it as fun as I do. And I hope this encourages you to try more. Again, the slides are on slides.com/myname, and the GitHub is github.com/myname. You can clone it and
Something about the network performance, by the way, multiple containers
yeah.
on a single host. How's that?
my man over here is going to work on that for us. And that's Rob, but he's an intern, but he's doing really good stuff, which is we're going to do, we have workloads for OpenShift, which is many thousands of containers, and JMeter, distributed JMeter infrastructure that was just pounding these web servers, Tomcat and JBoss and LampStack. And we're currently, and by we I mean him, is migrating it over to Docker-based backend, and we're going to throw the same load at it. So that'll be, let's just say, N containers. And we'll take it piecemeal until, like everything, like a piecemeal approach until we find a maximum. Kernel panics, whatever happens, and then we back it off. And I think the marketing people divide by 3, and then that becomes the supportability limit.
Is it just even a performance issue, or are there scalability issues with just having lots of containers?
Yeah.
Copy and write limits.
Yeah, there's limits. Yeah. The first ones we found were networking related. Okay, so if anyone needs to get home, I won't be offended, but I'll let you know that the lowest limit we found was with the bridge. And the reason is because the spanning tree protocol, the spec requires, I believe, 12 bits of an Ethernet packet header for spanning tree information, which means there's only so many fields size left, bytes left, to express the number of ports that are attached to a bridge. That number is 1024. So anyone who Googles for maximum number of containers on a guest, on a host, is going to find ultimately 1024. That's why we're looking at OVS.
So we can, I guess, get to a much higher number.
Yeah. I don't know if anyone wants to run it. Is 1,000 interesting? Is 1,000 enough? 5,000?
Is one thing, but performance impact is the other thing, right? So when you have like maybe not 1,000, but with with a double-digit containers, but when you turn on the bridge or turn on OVS or the bare metal, what's the difference in that kind of more typical scenario?
Yeah. So what we did was, okay, so it wasn't multiple containers, but it was multiple flows that we did. And so in that way, the numbers were just on top of each other, just like that. So even though it was not testing multiple namespaces, this is all stuff that's going to happen. I apologize. I don't have all the answers because it's all underway at the moment. But anyway, we did multiple flows, multiple netperf streams, and yeah, the overhead was in those are the general numbers that I'm kind of comfortable with right now.
Publish that data when the data comes out.
I don't think so. We will publish all the tuning.
Now that kind of information will be easier to obtain though, just the bare metal kind of tests something I've done with just multiple parallel flows, processes.
So if you get the netperf, if you download netperf, there's a contrib directory in there that includes a script that fires off a number of flows, and so it'll take about 5 minutes to get that number.
No, but I just want to compare with what is out. And that was different.
Yeah, it has to be done. It's worth doing. I just don't know what we're going to share and what we're not. Because usually what ends up happening is our partners, we partner with everybody at Red Hat, so they end up publishing the stuff. Cool. All right. Thanks, guys.